In this video, we're going to look at how to extend that Biot-Savart law to some different types of current configurations. So in the previous video, we had considered our line current, or as it's sometimes referred to, a filament of current. And so this is represented by this blue curve on the far left, so just some line that has a current I. And so as we saw, what we did, if we wanted to get some differential current, we considered some differential segment of this with length dl, and we said this had some differential current, which was I dl. We also have two other types of configurations that we can talk about. The first is our surface current, and so our surface current is going to have some surface current density. So surface current density, which is going to be given by capital K, which is a vector quantity, and dimensionally our K is going to be equal to amps per meter. So if we come down here to this middle representation here, so this is sort of like a plane, so a sheet, which is going to have some current in it. And so maybe our current K is going to be in this direction. So again, the K is that current density on that surface. So in this case, if we want to talk about a differential current, we're going to need a little patch of this plane. So some differential surface here. And so the differential current is now going to be K times ds, where ds is a differential surface area. And so note now the vector is associated with the K, as opposed to previously it was associated with our dl. The last type of current configuration we can have is our volume current. And so of course we're going to have some volume current density. And this is going to be the familiar current density J that hopefully everybody is used to working with by now. So this is represented by our J, which of course dimensionally is amps per square meter, or amps per unit area. So if we come down here on the far right, I have some three-dimensional structure, and so we're saying that this could have some current density J flowing through it. So this is going to be J. And if we want to consider a differential current, we need to consider some three-dimensional differential volume. So I can try to draw a small little cube in here. So that's a pretty rough looking cube. But hopefully we get the idea. Let's actually try to do that a little bit better. All right, not getting much better, so. Well, one more go. One more go at this. Let's zoom in and see if we can't get this. So let's get a nice square to start, and then we have something that looks like this. Okay, not much better, but you get the idea. We have some little differential volume in there, and that's going to give us a differential current, which is J times the differential volume, dV. So now for each of these structures, we have our differential current. So we know how to represent differential current in each of those structures. So what we want to do is we want to go back to that equation for our differential magnetic field intensity, dH, that we had in the previous video based on our Biot-Savart's law. And we want to adjust this a little bit. So of course this was for a line current. So we had our differential current given by this piece here. And so this is really just two forms of the same thing. And we're going to use this same basic form and adjust it for our other two configurations as well. But let's start for our line current. So if we have a line current, then all we have to do to go from this differential magnetic field intensity to our total magnetic field intensity is to integrate over the line. So we say our H is going to be the integral over the line of that I dl cross our unit vector in the r direction divided by 4 pi times r squared, where remember the definitions we had in the previous video, the unit vector in the r direction is the distance from our current carrying filament to our observation point, and of course the capital R in the denominator is the magnitude of that distance. So that would be how we find our line current, or we would find our H due to a line current rather. So we can also do the same thing for our surface and volume currents. So let's look at each one of those as well. So for our surface current, same basic approach, except now we're going to be integrating over the total surface, and we also need to change that differential current. So now instead of having I dl for our differential current, we have K ds. So that's the only adjustment we need to make. So we have now K times the differential surface cross U of R divided by 4 pi r squared. And then finally for our volume current, the same basic approach, of course, we have our magnetic field intensity H is equal to the integral over the volume. And again, we're going to adjust that differential current. So for our differential current in the volume, we said that's equal to J dV. So substituting that, and so let me get rid of these equal sign here. So we have our J dV cross unit vector in the R direction divided by 4 pi times R squared. And so one thing to note too is, of course, with any of these, we could use this alternate form where we have R divided by R cubed as opposed to the unit vector divided by R squared. And so this should look very familiar to you because we did something extremely similar when we were considering Coulomb's law and different continuous charge configurations. And so if you actually compare to page 120, you can see that similarity sort of as a refresher if you had forgotten some of the Coulomb's law stuff. And the basic approach we're going to take is, of course, for a particular problem, we're going to need to figure out, of course, limits on our integral. And for instance, if we're looking at this first case, we're going to need to figure out what is our dl, what is our u of r, and of course this distance r. So similar thing down here, what's our ds, what's this r direction, what's our r. What's our dv, what's our r direction, what's our r. And of course we're also having to figure out the limits on our integral in all three of those cases. So in the next few videos, we're going to look a little closer at some line currents and see how we can apply this general equation to get an expression for our magnetic field intensity H.